Okay, let's dive right in. We're about to explore one of the most beautiful and, frankly, mind-bending ideas in all of theoretical physics, conformal field theory. It's a concept that really makes you question our basic ideas about space and size.
So let me just ask you this. What if the universe didn't have a ruler? Imagine a world where the laws of physics are exactly the same whether you're looking at the tiniest subatomic particle or the largest galaxy cluster. This one single question, well, it's the very heart of what we're going to unpack today. Yep, that's what we're talking about. We are stepping into a corner of physics where the idea of a fundamental length scale, a smallest possible chunk of distance, it just doesn't exist. It's a world that's governed by a really unique and powerful kind of symmetry. So what exactly is a conformal field theory, or a CFT for short? Well, it's a theory where the physics looks identical at every possible length scale. If you could zoom in forever or zoom out forever, the underlying rules would never change. Now, this has a really big consequence. These theories only work for particles that are massless, like photons, and they have this special symmetry where angles are always preserved, even while distances get stretched all over the place. Okay, so let's dig into what angle preserving really means, because this, right here, is the mathematical core of what makes a theory conformal. The best way to picture it is to think about a map on your phone. You can pinch to zoom in or zoom out, right? The distance between, say, New York and Los Angeles changes like crazy on your screen, but the 90-degree angle of a street corner in Manhattan, that stays exactly the same. That is a conformal transformation in a nutshell. And here, believe it or not, is the math behind that map analogy. Now, don't let the symbols freak you out. All this equation is saying is that the metric, which you can just think of as the rule book for how we measure distances, gets multiplied by a local scaling factor, this little omega squared thing here. It's like having a different zoom level at every single point in space. This is what lets you stretch distances all you want while keeping those angles perfectly locked in. So, as you can probably guess, handling these kinds of transformations can get super complicated. But physicists came up with an incredibly clever, elegant mathematical trick to simplify the whole thing. And this works especially well in two dimensions, which, by the way, is why CFT is basically the language of string theory, since strings trace out a two-dimensional surface. The trick is to temporarily jump into something called Euclidean space. It's basically a mathematical playground where time gets treated just like another dimension of space. And why do we do this? Simple. It just makes the math so much cleaner, so much more elegant. It's a total game changer for doing the calculations. And this is where the real magic happens. In this nice, flat 2D space, we can describe any point, anywhere, with just a single complex number. That's it. This one little number, z, holds all the information about a point's position. It's incredibly efficient. And this is the payoff. This just brilliantly shows you the power of that little trick. You see that complicated metric transformation on the left, the one we saw a few slides ago? Well, with complex numbers, it becomes that beautiful, simple equation on the right. Any conformal transformation you can imagine in 2D boils down to just changing z with some function of z. Come on, that's an absolutely incredible simplification. Okay, so we've got this amazingly powerful symmetry, and we've got a simple way to describe it, but how does this symmetry actually connect to the real physics of a system? Things like its energy and its momentum. To answer that, we have to look at what's called the stress-energy tensor. Now, I know the word tensor sounds a little intimidating, but for now, just think of it as the master blueprint for a physical system. It tells you absolutely everything you need to know about where the energy is, where the momentum is, and how it all flows and interacts. So here's the crucial point. This deep, fundamental, conformal symmetry, it has to leave some kind of unique signature, right? A kind of fingerprint all over this energy blueprint. If we can find that fingerprint, then we know for sure that we're dealing with a CFT. So what is that fingerprint? How can you just look at the stress-energy tensor for a theory and know, without a doubt, that the theory doesn't care about length scales? What's the smoking gun? The answer is so simple, it's profound. The signature isn't something complicated being added to the theory. It's about something that's missing. The stress-energy tensor has to be traceless. And this equation right here, this is it. This is the proof.
Taking the trace is just a specific mathematical operation. Think of it like adding up the diagonal entries in that big energy blueprint. In a conformal theory, that sum is always exactly zero. If this condition is met, the theory is guaranteed to be perfectly scale invariant. It's the definitive fingerprint of a world without a ruler.
So let's just do a super quick recap. Conformal theories are all about being scale invariant. They have no built-in ruler. We learned that in 2 dimensions, the secret weapon to understanding them is using complex numbers, which makes the math just beautiful. And finally, the dead giveaway, the smoking gun that a theory is conformal, is that its stress energy tensor is traceless. And that just leaves us with a final, pretty wild thought to chew on. You see, many physicists think that our universe, at its most fundamental level, might actually be described by a conformal theory. And if that's true, well, what does that say about reality itself? What if, at its very core, the universe has no concept of size? What if scale is just an illusion, an emergent property that only exists from our limited point of view?